Hey everyone, I'm Brian Cantrell. I'm the CTO of Oxide Computer Company, and I'm going to be talking about Rust, Wright's Law, and the future of low latency systems. I'm actually going to be talking about those in reverse order. So let's actually talk about systems performance here and low latency systems and the history thereof, as I am wont to do. Now, if I have to say it, software runs on hardware. Hardware is the ultimate actual arbiter of our system's performance. Hardware is the thing that actually runs our systems. And even though hardware is not the beginning and end of all systems performance, certainly, it will ultimately limit our performance. So I like to take a hardware lens and look up through a system when we look at systems performance. And if we look at the history of systems performance, we can see three different kinds of revolutions that have really advanced systems performance. One, and the best, we'll talk about these a little bit, are process revolutions. And by process, I don't mean process in the Unix sense or process in the kind of the workflow sense. I mean process in the semiconductor sense, semiconductor process. And semiconductor process revolutions are the best because they advance truly everybody. And we're going to talk about our favorite revolution for a little bit there. The second kind of revolution is an architectural revolution. And I don't mean architectural in the kind of the building sense. I really mean architectural in the computer architecture sense, changing the way we organize our system. And those are generally optimized for, those revolutions are extremely important, but they're optimized for certain use cases that we've observed that certain kinds of applications do this kind of thing. We can make them perform much, much better if we change the way we architect the system, change the building blocks that we've got. Those are also as important. They're not quite as unequivocal. They don't raise all boats, but they're also extremely important. And then finally, we've got software revolutions, which honestly is what a lot of us focus on. And those software revolutions really boil down to how can we better utilize hardware? We don't always phrase it that way, but when we advance performance with a software revolution, we are advancing performance because we're using hardware better. And we're going to work up to what I think is a very big revolution in terms of software, which of course the title gives away a little bit. And of course, all of these revolutions have to exist in the confines of economics. It's very tempting as engineers to divorce economics from technology. And we want to think that if we invent a better technology, that it will naturally, especially one that yields a higher performing artifact, then of course everyone is going to run the higher performing thing. Well, not if it's economically unsustainable. So economics ultimately looms over all of this, but these are the different kinds of revolutions. And of course, we talk about process revolutions, we got to talk about Moore's Law. Moore's Law was an incredible guide, gift for our industry. It was an observation that Gordon Moore made in 1965. I really recommend, if you haven't, reading his original paper is amazing. It is so prescient and actually kind of funnily, it does not contain Moore's Law itself. Moore's Law is not actually described in that paper. He just made a bunch of really, really, really good observations about economics, about transistor density, about performance. And the term actually Moore's Law postdates the paper. Carver Mead, the giant of VLSI, actually coined Moore's Law many years after the fact, in 1971. And Moore then updated his law in 1975. It's like, well, as long as we're talking about a law, let's actually phrase this a little more concretely as a doubling of transistor density every 2 years. That kind of became every 18 months. But people naturally conflate Moore's Law actually with the other things that he observed in the paper, namely that transistors were getting denser, they were getting faster, and they were getting cheaper all at once. Density, speed, and economics. And like, wow, it was great. And there was this long period of time where Moore's Law was just like awesome. The good old days of Moore's Law. This is like when I was coming up, maybe when you were coming up too, when Moore's Law was so incredible that a computer would get twice as fast 18 months later. You'd go get a new computer, and the one you bought just 18 months ago, just 2 years ago, is obsolete. And in fact, it was getting so fast, so quickly, that we actually had to slow computers down in order to play software, play games that was written for, or that were written for the old machines. So you would buy a game that was written for a PC-AT, and the thing would be unplayable on a 386 SX. Sorry if I sound like Antiques Roadshow here. If you're of my vintage, you know what you're talking about. We added, and I do think this is genius, when the button to make it go slow was not called the go slow button, it was called the turbo button, and it was always depressed, which I think is genius. But you see, you could undepress the turbo button to make your application go slower. Even in those days, though, and as the 80s gave way to the 90s, Moore's Law was actually, the CPUs were continuing to get denser and faster. We still had Dennard scaling, which was great. Our clock rates are going up, but DRAM was not getting any faster, and we were increasingly hitting the memory wall in the late 80s and especially in the 90s. And yes, caching was helping. Caching invented on the IBM 360 Model 85 in 1968. Originally called muffers, memory buffers, kind of interesting historical artifact, renamed to caching. Thank you for that, the editor of the IBM Systems Journal who suggested that. Caching, hugely important architectural revolution to avoid that memory wall. But the memory wall, we were indisputably hitting it, even with caching. And by the time we got to the 90s, like, yes, Moore's Law was continuing. Transistors were getting denser. Dennard scaling was still continuing. But we had more and more applications that were simply bonking up against that memory wall. And we actually had to have a big architectural revolution. Indeed, the big architectural revolution when I was coming up, when I was coming into the industry, maybe you too, was symmetric multiprocessing, SMP. Adding different CPUs. So now we're saying, okay, we actually can't make a single CPU that can run this entire system. What we can do is multiply the number of CPUs. That was a big revolution, but it necessitated, as an architectural revolution, it necessitated a software revolution. We had to make our code multi-processed. We had to make our code multi-threaded. We had to make our system, we had to optimize our systems for throughput. This actually did little for single-threaded latency, honestly. A lot of experiments in there trying to improve single-threaded latency, things like deep pipelining, VLIW, very long instruction word, as they say, you haven't heard of it for a reason. These were basically failed experiments. Increasingly, Moore's Law was giving us more transistors, but it was hard to spend those transistors. So even the good old days were kind of becoming a real challenge. We go through the 2000s, and now we get into the 2010s and the last decade or so, and Moore's Law is very clearly decelerating. Dennard scaling stopped in 2006, so we had left Dennard scaling way behind. You're not running a 5 gigahertz or 10 gigahertz or 20 gigahertz CPU because the physics doesn't allow it. We have settled on a clock rate that's between 1 and 4 gigahertz, and we have found different ways to spend that silicon. We are spending that silicon with multi-cores. We're getting many cores on a die, but that process revolution has indisputably decelerated, and you're kind of seeing one after another companies really struggling to shrink that process node. And as actually, when we talk about process nodes, you talk about 7 nanometer and Intel talking about between 14 nanometer and 10 nanometer, and then getting to 5 nanometer if you've got an M1 that's a 5 nanometer process. Ultimately, we're trying to get to 3 nanometer. You may be wondering, if you're a software person, it's like, okay, we're talking about these nanometers, like 7 nanometers, 5 nanometers, that seems really small. What are we talking about? What does 7 nanometer measure? What does 5 nanometers measure? And I view it as my professional responsibility, and I'm sorry to go on a quick tangent here, but I view it as my professional responsibility every time we talk about nanometers in terms of process nodes. We also have to say that it's a total fiction. I think this is completely irresponsible of the semiconductor industry to leave us with the impression that those nanometers are a unit of measurement of anything, because they're not. A silicon atom itself has got a van der Waals radius of about 210 picometers. Clearly, we could not have a 3 nanometer transistor. Nothing could actually be 3 nanometers long. We're not going to have something that's 15 silicon atoms or whatever. What those things are actually trying to express is density. They're expressing transistor density, and it doesn't actually mean anything. What they did is they took a process from a long time ago and they said like, well, that was a much less dense process, and we take the density now, and what would be the effective nanometers if we kind of scaled that? And you're like, oh my God, that's ridiculous. Anyway, so it's not you, it's them, it's the semiconductor industry. They've got really misled us all into thinking this physically is measuring anything. It's not. 7 nanometers is about 100 million transistors per square millimeter. I really wish they would speak in terms of millions of transistors per square millimeter. It would make it a lot easier, be a lot more accurate, but they're not. So look, suffice it to say that the process node is a rough measurement of density, and you can roughly assume that a 7 nanometer process is roughly twice as dense as a 14 nanometer process, but don't assume anything else. So my apologies on behalf of an industry that I'm not actually even in. But Moore's law has decelerated. And in particular, Gordon Moore's observation in 1965 is really this economic observation that these things are getting cheaper over time, in addition to the density and the performance. Moore's law is no longer an economic law. In terms of how much that 3 nanometer, that 5 nanometer transistor costs, it costs a lot because we've got to build this huge fabrication for it, and we kind of scrap this old node. Well, is there another way of looking at it? And there's actually, Gordon Moore is not necessarily, even though Gordon Moore is great and his 1965 paper is amazing, he's not the only one to kind of look at the history of technology and wonder about its economics. And in particular, in 1936, this guy, Theodore Wright, who worked for an aircraft company, and no relation, I understand, to the Wright brothers. That's a coincidence. But Theodore Wright worked for Curtiss, and he was looking at the cost of aircraft over time. And what he noticed actually is that as production increases, the unit costs drop. And in particular, when the volume roughly doubled, the unit costs dropped by 10 to 15%. And this is pretty interesting. What this is basically saying is like, we get better at stuff. When the more stuff we make, we get better. There are just pure economies of scale, but there's also, it's know-how. We're making more of it. We're getting better at it. We're finding process improvements. A bunch of little iterative stuff that adds up. And that adds up to this really significant law, Wright's law. And in 2013, Jessica Transick and her crew at the Santa Fe Institute observed that actually Wright's law has actually even better predictive power than Moore's law to explain what happened to the transistor economics over time. And in particular, Moore's law is ending, but Wright's law seems to be holding, especially for older process nodes. That is to say, the amount that we are spending per transistor does seem to continue to be dropping. And we are making more and more and more transistors. And this is really interesting because there are lots of ramifications for this. If Wright's law continues to hold, Moore's law has ended, but just like Dennard's scaling ended while Moore's law held, transistor density held, if Moore's law ends while Wright's law holds, it will have real ramifications for us. In particular, we are going to have compute be economically viable in more places. We are going to be able to put compute elements, stored program computers, Johnny von Neumann's gift. We are going to be able to put that in more and more places. This is true even on die. You look on die, right now we've got lots of course, core complexes that are actually running the workloads that we know about. But there are also a bunch of other cores on there. Chiplets have made it possible to take cores that are actually on a different process node. Part of the reason that AMD was early to chiplets was their need to combine a 14 nanometer process node and a 7 nanometer process node onto the actual same die, which they said the I/O package on there, the I/O chiplet, is actually a different process node than the core complex, which is actually a really interesting innovation because now the die becomes this entire computing system. So quick, how many cores are on your server? The answer is you don't know, because I don't know. What you know are the core complexes that you're aware of, but there are a bunch of hidden cores on there that are actually responsible for hydrating this whole system that you don't necessarily see. Those are the gifts, per se, from Wright's law. There are lots of performance ramifications from this, because in addition to just beyond the die, we are going to be able to put cores in more and more places around the broader compute ecosystem. We're already seeing this happen. We're putting compute close to the wire with smart NICs. That's what a smart NIC is. A smart NIC is taking a compute element and putting it right next to the wire. I don't actually need to go over to PCIe to talk to a host CPU to get it involved. I actually have got a compute element I'm attached right to the wire. Open channel SSDs, same idea with raw flash. On spindle compute, where you've got an actual compute element that's sitting on the spindle. All of this stuff is going to serve to lower latency. You're going to be closer to where the actual action is happening, and you're going to be able to act on that faster. This is important. The other aspect of this is not just low latency, but also high throughput, where we're going to take data and we're going to march it over to special purpose compute, GPGPUs, FPGAs, where it actually pays the freight to get it all the way over there, because we're going to be able to compute over there so much more quickly. We see that certainly with MLDL today, where it makes sense to actually haul it over there because we can perform it so much more quickly on that special purpose compute. But in this world, security and multi-tenancy cannot be an afterthought. One of the constraints that we have now, that we live in a secure multi-tenant world. We have to. This requires us to rethink our system software very fundamentally. And I'm going to do something that I very rarely do in my own talks, namely tell you to go watch another talk. I think I've done this with James Mickens before. You should always watch James Mickens' talks, are terrific. And I'm going to tell you to watch Timothy Roscoe's incredible OSD 2021 keynote, where Timothy is calling on researchers in the OS community, hey, we've got to rethink things here. And these red lines that he circled here are all of the cores that researchers aren't thinking about. We need to rethink the way that we think about our systems to actually hydrate these hidden cores. This coming revolution, where we've got many compute elements in many different places, is at some very deep level special purpose. These compute elements are almost tautologically special purpose. Our general purpose compute is still going to be that big core complex running on our host CPUs. That's going to draw the most power. That's going to have our highest performance. That's going to be connected to our fastest DRAM. But we are going to have these compute elements around there that are special purpose. Because they are special purpose, they're going to be weird. And in particular, they are going to have more compute. They're going to be out of balance with respect to memory and with respect to storage. These things are not going to have much memory, and they're going to have very little non-volatile storage, especially non-volatile storage that they can actually write dynamically. So in that world, in these very confined worlds, the dynamic environments like Java and Go and Python, et cetera, are non-starters. And honestly, like the development benefits that you get from like Python are like, it's kind of questionable, because these are like programming your calculator, these things out there. If you're SmartNIC or your Spindle or your Flash. The languages that we've traditionally used in this domain, C and C++, we could get them to work. We know that, but C and C++ have really well-known challenges and that I almost certainly don't have to elaborate on. Trust me, I spent 25 years as a C developer. I love C. I am a conscientious objector of C++, but I do love C, and I am at the end with C. C has taken us as far as C is going to take us, and enter Rust, and in particular, its killer feature. The killer feature of Rust is no standard. In this domain of special purpose compute, Rust has this incredible ability to not depend on its own standard library. And a lot of what's actually valuable about Rust is not in the standard library. Some types, algebraic types, the ownership model, traits, hygienic macros. Oh my God, hygienic macros are, if you are a dyed-in-the-wool, dead-ender C or C++ programmer, you need to get into hygienic macros in Rust. Trust me, you're going to love it, the power that you can get from hygienic macros. All of that stuff is in core, not in the standard library. So we can have these no-standard crates that use the vast majority of the power of the language. And in particular, a no-standard crate cannot perform a heap allocation. It's enforced at compile time. And this is amazing, to have something where I can actually truly have composability at a layer of the stack that has never had this kind of composability. This is incredible, to be able to pull in different no-standard crates and actually pull together a system. And the binaries are tight. So at Oxide, we're actually developing our own new operating system, soon to be open source, which it's a new operating system, so appropriately we call it Hubris. Hubris is a message-passing microkernel-based system, memory-protected system, entirely in Rust, Rust microkernel, Rust tasks. And our minimal hubris system is 30K. We have entirely realistic systems that seem pretty big at 200K. And that's without really attempting to optimize for it. That's pretty amazing. You can shove that into a lot of different places, and those tasks then you've reserved all of that compute power for the tasks you want to run, and you can do that in a way that's memory protected and safe. It's pretty amazing. No standard is, as far as I'm concerned, really without precedent, and Rust is actually the first language since C to meaningfully exist at the boundary of hardware and software. And this is what points us to the future. Wright's law means we're going to have compute in more places. We are already seeing that. Those compute elements are going to be special purpose. Don't wait for your general purpose CPU to be shoved down to a SmartNIC. It's going to draw too much power. We can't have memory that fast down there. But what we can put down there is Rust. Rust can fit into these places. And what we are going to see is many more exciting de novo hardware-facing Rust systems that, thanks to no standard, will be able to build on one another. It's a very exciting time to be developing high-performance, low-latency systems, and the Rust revolution is very much here. With that, thank you very much.